Today's lesson is going to be part of 21B, where we talk about B cells and T cells. But before we go any further, are there any questions from any of the other materials that we went over?
Oh,
Speak now, forever hold your peace. You sure? Okay. All right. We're talking about B cells and T cells. So here is one quick slide to remind you. They're both lymphocytes, so they look exactly alike. All righty? But they have two totally different functions. Their job is to get rid of antigens, bad guys. Okay? B cells, they attack the invaders while they're still outside of your cells, while they're still in your lymph and in your blood. Why? Because B cells make antibodies that stick to the outside of a bad guy who's floating around in your blood and lymph. 10-4. But what if the bad guy, a bacteria, a virus, has already entered a cell and has started hijacking that cell to make more proteins for bacteria or for viruses? That's when the T cytotoxic cells come in. They attack the invaders that have gone inside your cells by killing your infected cells. Got it? That's why they're called cytotoxic. They're not toxic to the bad guy cells, they're toxic to our cells because they feel that our cells are harboring a bad guy. Make sense? Okay. All right. Let's see. Training. Well, okay, just as a review. Remember we talked about, I think last time, the epitopes or the antigenic determinants are the outside proteins of an antigen. So it doesn't have to be the bad guy, it's just a piece of the bad guy that these Y-shaped antibodies are specifically designed to attach to. Got it? That's why all antibodies are proteins. Why? Because proteins come in shapes. Got it? We have billions of different B cells that can make billions of different shaped antibodies. Got it? And it's the shape that counts. Got it? That's how they make contact. That's why, see, triangle shape, rounded shape, square shape. Alrighty? And therefore, one bad guy could have multiple antigenic determinants or epitopes on the outside, okay? On the surface, epi, like epidermis. And that's what the antibodies stick to. Yes, sir? Okay, good. All right. So B cell and T cell training. We do need to make sure that we understand that it's part of the third line of defense. Quick review. The innate defenses, the ones you're born with, the ones that are non-specific, they don't care who the bad guy is. First line, stop them from coming in. Second line, stop them from spreading. Again, non-specific. The feeder doesn't care who the bad guy is. Natural killer cells don't. Phagocytes just eat, okay? And of course you have your antimicrobial proteins and inflammation, like complement and interferon, okay, which I'm sure we talked about last time. But when we get down here, what is so special about this? Three things. Number one, they include your entire system, okay? When the B cells and the T cells are involved in the fight, it's systemic. Number two, they are highly specific. As we said, there is one B cell for this shaped bad guy, one T cell for this shaped bad guy, okay? And third, memory. They have a memory of meeting and fighting this bad guy, okay? And from this memory, we actually have created what we call, what? Vaccinations, got it? Where we introduce a piece of the bad guy, wake up, activate these characters, and now when a new version, or that polio comes back as a real polio virus, you've been immunized against polio, and this will create an army. The memory cell will be turned into an army to fight it off. Okay? All right. So we're talking about training, and this is why we need to know. Both are made in the bone marrow. The T lymphocytes go to the thymus gland. The B lymphocytes stay in the bone marrow, and that's where they're trained. When they are trained, meaning they can recognize self and non-self, when they are done with school, we say they are naive. Got it? Why? Because they have not made contact with their specific antigen yet. But they have the shape on their receptor for it. Got it? It just has not made contact. 10-4? So that is called being naive. Once you make contact, you are now activated and you do what you do. Cytotoxic cells kill, B cells make antibodies. T helper cells run around like Paul Revere and tell everybody the British are coming. All right? Now, when you are coming out of school, yes, you're naive, but I forgot to say, you are immunocompetent. You are competent to do your job. You have the right receptor to be able to recognize self and leave self alone, and to recognize only the one bad guy you're supposed to recognize. Okay? All right. T cell versus T cell. That's old school. All right. So let's make sure we understand about school, and that's why you're going to see some of these bold print words on my test. All right. When T cells are in school, the first thing they do is they go through a series of what's called positive selection. What is positive selection? We want you. Got it? That's what positive means. I want you. So they introduce a self protein to all of these new recruits, these new T cells. And every T cell that can recognize self, you move on. Oh, you don't recognize self? You're killed. Got it? We don't want you. All right? And because we want you to be able to be what? Self-tolerant. You've got to be able to recognize what self is. Otherwise, you might think self is a bad guy, and now you have an autoimmune disease. Does that make sense? Okay. And guess what? If you don't pass this part of the test, you get killed by apoptosis. You're given a genetic programming that says, stop dividing. Okay? So that's positive selection. Those who make it through that go through negative selection. What does this mean? That means we are going to go against you if you do something. So again, we'll show these new recruits a self protein, and any T cell that overreacts to self, oh, that's self, oh, that's self, you get killed. Because we're afraid that if you get released, you might overreact to self and make an autoimmune disease again. Okay? Well, yes, sir.
So between positive and negative selection,
Yeah.
when you say it would overreact,
Yeah.
well, if it recognizes that it's a self protein, what would it be reacting to? Because
I don't know. It just says it overreacts, so I'm not really sure what the overreaction is. It might be an overreaction to the point of maybe we should kill this.
Okay.
Got it? It overreacts to self. Like, oh man, wow, we really need to get this.
So it's basically like a more selective version of the positive selection.
Mm-hmm. Yeah. And so again, if we overreact, you get killed. Got it? So, what percentage don't make it through school?
98.
98%. Only 2% of the T cells make it through T cell school. Because, the body knows how incredibly important it is that you don't overreact and don't attack self. Because we call that an autoimmune disease. Okay? If you do that. All right? Okie dokie. So only the 2% survive as immunocompetent. All right? So that's what happens in school for T cells. Now the school for B cells, a little less understood, but if a B cell isn't doing its function, the clones are deleted, the copies are deleted, or is deactivated, not energy, but anergy, no energy. So those are, again, words. If you see the word anergy, you know it's a B cell school, not T cell school. But here's the cool thing. Some of the B cells that don't make it through go to reform school. They get a second chance. It's called receptor editing. What does that mean? We'll shuffle the genetics of that B cell so it has a new receptor, a new shape, okay? Maybe that shape will work better, okay? It allows the B cell to change their receptor proteins and become self-tolerant, not overreact to self, all right? And the school is what allows you to become immunocompetent. You're naive until you make contact, and then when you make contact, you're activated, okay? Now, I know there's a test question about this, so that's why we need to know it. It is our genes, not the antigens, that determine which foreign substance we see. You are born with this kind of receptor or this kind of receptor. Got it? And if that's the kind of receptor that works, perfect. Got it? And that's why health and sickness sometimes runs in families, because there's a genetic component. I think I say in my video, have you ever heard of a family that seems to get the flu every winter? And some families who seem to never get the flu ever? That's because the family that doesn't get the flu, their genetics can recognize more antigens. Got it? They can make 1.5 billion more, okay? Whereas the family that seems to be getting sick makes less than 1 billion different shapes. So there's going to be some shapes that they don't recognize, and therefore they can't help fight. Does that make sense? So,
if they can't help fight it, then the only way to treat that would be with medicine.
Yes, exactly. Right.
Left alone, their body would not be able to do anything.
Right. Okay? And that's why some people don't make it. Does that make sense? Okay, so, but because this is modern society, what do we spend most of our federal energy doing? Making vaccines and making medicines and things to help those people. Does that make sense? We're not in a society that says, oh, you can't handle it? Go ahead and die. See you later. Got it? We've progressed past that.
If they don't have the right receptor
to recognize
it, when you get a vaccine, does your body would then make that receptor, or no? You still wouldn't do anything.
That's the way I look at it. That's the way I see it. That if you don't have that ability to make that receptor, you don't have that ability to make that receptor.
Okay.
And, the thymus, the school, your thymus is this big when you're a baby. It's this big when you're a kid. It's this big when you're an adult. Got it? So when your T cells going to school? When you're younger. And that's why the more you have a chance to get in contact with bad guys, what do kids do? Everything in their mouth, right? Well, that's actually nature's way of introducing little pieces of bad guys to your system to activate the B and T cells that are designed to see those bacteria. Got it? So then when you actually get a lot of bacteria, like through a cut or whatever, you'll have an army ready to attack and kill them. Okay? And you don't have to worry so much of getting sick. And we realized that, so we created vaccines like polio vaccine and MMR to give to kids. Got it? It's a heat-treated virus, so it can't multiply. It's been damaged, but it's got the shape that will fit the one receptor of the one B cell and the one T cell that you have. So now you've been activated, and if the real polio or the real measles comes along, we can stop it. Okay, your body is now activated and ready to stop it. Cool beans? All right. APC. What is an APC? Well, I'll just say it very quickly. Antigen presenting cell. What is that? It's a macrophage. Pac-Man. It eats a bad guy and puts a piece of the bad guy on its surface. Got it? So that a B cell and a T cell can feel and say, oh, that's the shape of the bad guy. And then they can run around and say, hey, that's the shape of the thing we need to be careful for because it got eaten up over here. Think about it. One virus come into your body at a time? Only one bacteria? No. So if one virus got eaten or one virus one bacteria got eaten and a piece of it's on its surface, you can be sure there's plenty more. But by doing that, the antigen presenting cell is like showing the B and T cells what the bad guy is. Does that make sense? It's eating a piece of it, eating the whole thing, and put a piece of it on its surface to help recognize what the bad guy is. Okay? And who are these APCs? Well, neutrophils, monocytes, phagocytes, dendritic cells, which are big eaters with the spikes sticking out of them. Okay. All right, that's an APC. And now we need to know, MHC type proteins. I call this a basket. This is a basket on the surface of your body cells or a basket on the surface of the APC. And in that basket is a protein that you have eaten if you're an APC or that you have made if you're a body cell. All right? And that's where we have to understand what's going on. You've got two kinds of baskets, type 1 and type 2. Oh, here, let me show you. I like this picture. See? That's a dendritic cell. And what's he doing? Eating a bad guy. And he breaks the bad guy up and puts a piece of the bad guy in a little basket. Got it? And here comes a helper cell, reaches into kind of an unfortunate reach into this basket. But he's reaching for the basket and said, aha, that's the shape of the antigen that's attacking us today. And like Paul Revere, he runs around to tell everybody, that's the shape, folks. See, if my receptor fit it, so that's the shape of the bad guy. And that's what he does. He's activated now, and as a helper cell, he runs around telling everybody who the bad guy is. Got it? You see, we're going to find out as we go through this. See how I like to jump around? What is HIV? HIV is a virus that kills who? Helper cells. So if these guys are gone, is there anybody to feel this basket and to tell everybody what the shape of the bad guy is? And that's why you die of AIDS, acquired immunodeficiency syndrome. You die of something you've caught because there's no Paul Revere to run around and tell everybody that the British are coming. Does that make sense? That's why it's so devastating, HIV.
Will the helper cells always have the correct basket for the?
Do they always have what?
Will they always have the correct receptor?
Well, they all have one receptor of one shape. So if this is the one that fits, then yeah, it fits. This guy might have a different receptor. He's not going to be involved in this situation. Okay? So what you're hoping that genetically you can create 1 billion different T cells with 1 billion different shaped receptors to recognize 1 billion different shaped proteins.
And that's why kids put their hands.
Yeah, and that's why you want to wake up the ones before you actually get sick. You want to be introduced in little amounts. Okay? Now, I'm not pleased. I know I said this on the video. I don't mean go take your kid, throw them in a puddle, get them nice and dirty. No, just don't flip out if they do get some stuff in their mouth. Okay? Or if they play with the dog and stuff. Alrighty, because see, when we eat the bacteria, we're going to lyse it, poop out, but in the process, we're going to put a piece in that basket. Now, let's talk about the two baskets. This MHC protein, type 1s are found on all body cells. Type 2 are found on all APCs. Okay? So, they can either have a self protein in it or a non-self protein in it. Okay? I know this. I wish we had 6 students in like we did last night. I can demonstrate this, but I can still at least give you a little bit of a hint as to what's going on. You see, there's 2 kinds of baskets. Type 1 and type 2. Make sense? Okay. And you can have 2 kinds of antigens. A good guy or a bad guy. Clemson speaking here. All right. So, if I am a... Oh, I'll do this. Maybe this will help. Mr. Weber's always got toys. Okay. What am I?
Body cell.
I'm a body cell. So which kind of basket do I have? Type 1. Okay. Got it? So, if I'm a type 1 and I have this in my basket, and along comes, now, we got to make sure we have this under control. Who comes along to talk to a body cell about what's in my basket? Cytotoxic cells. Okay? That's important. Cytotoxic cells. So the cytotoxic cell puts his hand in here and goes, oh, that's a tiger. That's a self-protein. No problem. Body cell, I'll let you live. Because this is just a protein that I made, and it's on my basket. 10-4? Okay. Now, what if I have this in my basket? I didn't make this. I'm a Clemson Tiger. I didn't make no chicken feathers. Okay? So, that means there must be a gamecock that's invaded me and forcing me to make gamecock parts. Does that make sense? A virus got in. 10-4? And now I have a viral protein sitting in my basket. Here comes the T cytotoxic cell. Wait a minute, that's a foreign protein in that basket. And the only way a foreign protein gets into a body cell's basket is if the body cell has been what? Invaded. Well, I can't kill him because he's inside me. So what does a cytotoxic cell do? Kills me. It hits me with perforin, which drills holes inside me, and all my guts come out, including pieces of chicken parts. So that's how we get rid of this virus. Does that make sense? Okay. Now, what if I'm an APC? Okay? I have this kind of basket, right? Okay. Well, what if in this basket I had a Clemson Tiger? All that means is I ate a self-protein. You know, I ate up a dead piece of skin. I ate up a dead piece of tissue. That's my job. I'm a big eater, okay? Is that anything to be alarmed about? No, I'm supposed to eat this. So who is looking in this basket? A T helper cell. The helper cell says, oh, that's a self-protein. Hey, keep doing your job, APC. Bye. Okay. What if in this basket there's some chicken feathers? That means I just ate a gamecock. Well, the only way I could eat a gamecock is because the gamecocks are invading the body. So the helper cell goes, uh-oh, that's a gamecock. Quick, let me tell everybody, Paul Revere style, that we're being invaded by gamecocks. 10-4? So that's why we have 2 kinds of baskets on 2 kinds of cells for 2 different purposes. Does that make sense?
With the second basket for the APC cells, is that in the video where you talked about how you have the, like, let's say a piece of the virus protein, and then you have also a piece of self-protein, and that's how it recognizes that it's an APC and doesn't kill it?
It doesn't kill it, yeah.
Gotcha.
Okay, does that make sense? All right. So there you go. While you're chopping up, while the APC is chomping up a bad guy, a piece of the bad guy will be put inside the basket. All right? Okay. Just got to keep and remember, who is checking what basket? The helper cell checked the basket, type 2, on antigen-presenting cells, or big eaters. Okay, there you go. There's a helper cell talking to a big eater. All righty, let's see, what else? What's the next thing we need? We got APCs, we got baskets. Okay, primary and secondary response. Okay, let's do primary and secondary response. Come on, sit here somewhere. Ah, right here. Okay. Let me go back. All right. This is what happens. We're being attacked by these little round green guys. Got it? Doesn't matter what they are, they're bad guys. Okay? We're being invaded. They are the antigen. Well, look at these 3 B cells. Look at their receptors. That's a square. That's a half moon, and that's a V. Which one of these fits these circles? Only this one. Got it? So that's why hopefully we have a billion different ones with different receptors. Got it? As it turns out, this one is not useful here. Only this one. But as soon as it makes contact, okay, what's it going to do is multiply itself. Got it? And when it multiplies itself, it's going to change into what's called a plasma cell. Differentiate. Plasma cells release antibodies, which are these Y-shaped things with little receptors on the end of the top of the Y. Okay? Please note, don't these antibodies look just like the receptors? Because they are just like the receptors. Got it? With the exact same shape. All right? We make a bunch of them, and they land on the bad guys, coat them so the macrophage can eat them up. Good. Done. Finished. 10-4? That's only half the story. You see, we have to have a 5-day or so delay, and we only make this many antibodies. Does that make sense? What happens if even years later we come in contact with the exact same bad guy? Do we have to wait 5 days? No. Immediately, within hours, we start making antibodies. Do we only make this many or this many? See how many more we make? And does it immediately go down in about 20 days? No, it stays high for several months. Got it? To make sure there's plenty of antibodies to coat every bad guy that could possibly have attacked you today. And that's why one of the hardest things to understand, or to help people understand when you're a healthcare worker, is, hey, how do I know this vaccine is working? I didn't get sick. That's how you know it's working, because you didn't get sick. Does that make sense? You didn't get sick because we created an army to prevent the bad guys from taking over and making you sick. Alrighty? And that's why this is the primary and this is the secondary response. Okay? And all they're showing you here is that the IgGs make a bigger response than the IgMs. That's all. Okay? But another cool thing is, can I be fighting one bad guy and fighting a second one at the same time? Yeah, because every bad guy has a different shape, and every B cell and T cell has a different shape, so we can make clones of that one while we're making clones of the other one. 10-4? We can fight several battles at the same time. And when we found that out, we started combining vaccines. MMR. Got it? Mumps, measles, and rubella. Because they're 3 different shapes, therefore we know that the 3 different types of white blood cells will proliferate and differentiate and create antibodies. Make sense? Okay. All right, so we got that. Now, the 5 classes of antibodies. Here we go. 5 classes. Now, what does the I and the G every time mean? Immunoglobulin. Aren't they part of your immune system? Yes. Are they globular in shape? Yes. In fact, let me show you real quick. We always draw antibodies with a Y shape, but it's actually globular. See how what the glob it is? But it's called gamma because that's what a G in Latin looks like. Okay? That's a Roman G. It looks like a Y. So that's why they're saying this is a globulin, a globular IN protein that's shaped like a gamma. Gamma globulin.
What's a gamma again?
Huh?
What's a gamma?
This, a Y shape. Gamma is G, but it looks like a Y. Just like alpha is A and beta is B, gamma is G, okay, in the alphabet. Cool beans? All right. So, what do I need to know for my test? Just a couple of facts about each kind, okay? For example, IgG is the main class, and it's the only one that can cross the placenta. So, this is the one that mom would send across the placenta to kill the baby if the baby was Rh positive and mom was Rh negative, which is why we have to give mom a RhoGAM shot. Well, what's the Rh? Rh factor. What's the GAM? Gamma globulin. We're going to give her an antibody against her antibodies. If we can glue up her antibodies before they cross the placenta, we save the baby's life. That's why you get a RhoGAM. And O just is a letter they use to combine two words. Okay, RhoGAM. All right, IgA. One of the things, what did I say last night about IgA? How do you remember it? Guaranteed low prices, IgA. There's a commercial where a little cartoon man does that. Well, what's IgA? A grocery store. What do you do with groceries? Eat them. This is against antigens that are eaten or ingested. Got it? So where do I find this? In our saliva, in our mucus, and in our tears. Because these are three openings that are always open. Got it? You gotta breathe, you gotta see, and you gotta eat. 10-4? So bad guys can come into those three areas, so we have a bunch of IgAs there. Right? Now, where does a baby get food? From mom. So mom has it in her milk to prevent any bad guys from coming into the baby's mouth. Isn't that cool? All right. See, it prevents bad guys from attaching to the epithelial lining on the inside of your nose, eyes, and mouth. Okay? So that's IgA. So just think about the IgA grocery store. IgM. M, macromolecule, big. This is a big antibody that can glue the wrong blood types together. Got it? If you're A and somebody gave you a bunch of B, it will glue all the B's together. Because does an antibody know that a B blood is not attacking you? No, he just knows that it's foreign. Well, what do antibodies do? Glue things together. So a macrophage knows who to eat. You see, in real life, if you were to get into a scrap with an animal or a person, how much blood of theirs would end up in your body? A little bit. Well, it's easy. Glue it up, eat it up, done. Where it's dangerous is because now we can give you a whole bag of blood. And if we give you the wrong, we've now created a bag full of clots inside you. Is that healthy? No. So yeah, somebody had to find that out the hard way. And now we, thank goodness, do blood testing to make sure you're compatible with what you're being given. Okay? All right. IgE. This is the one that is released on contact with something you're allergic to. And the IgE then tells the basophils and the mast cells to release histamine. So you see the basophils and mast cells, which we talked about in an earlier chapter, yes, they put out histamines, but they have to be told that by the IgE antibodies. Got it? The IgE antibody says, hey, release that stuff. It causes those cells to release the histamines. 10-4? Now, IgD is not well understood. So is that going to be a test question? No. Okay. Make sense?
Can you go over the IgE again? I don't understand the
IgE?
basophil and the mast cells.
Okay, basophils are the white blood cells in your blood that release histamines. Now, what's the histamine going to do to your blood vessels? Open them up. If they're all open all at once, blood pressure goes to 0, you die of anaphylactic shock. Okay? Mast cells are in your skin. When mast cells release histamine, you get inflammation. Got it? Redness, swelling, remember? All that kind of stuff. So, I just want you to know that it's the fact that a B cell came in contact with the bad guy first, released IgA, which then tells the mast cells and the basophils to release histamines. That's all. Okay?
So the IgE.
So IgE tells them to release histamines.
Okay.
Okay? Cool?
Yes.
All right, so that's how those 5 work. All right, next thing, plan of attack. Okay, your book, and I've seen several other books say this. The plan of attack, all they mean is antibodies do 4 things. Got it? And it just happens to spell plan. All right? Don't freak out. It doesn't look like it all the time. But here we go. The P is precipitation. As I asked you last night, what's precipitation? Rain, Mr. Weber. Okay, well, that's kind of what we're talking about. It's water. But where did it come from? A cloud. So what is a cloud? It's water as a gas. When you put enough of it together, it congeals, it comes together, it precipitates into water. And it falls out of the sky because water is now heavier than gas. Alrighty? In your blood, what we're saying, what if it's a bunch of tiny little viruses, so small that your macrophages can't see it? But what if we glue all of them together so that the whole bunch comes out of solution as a solid? Got it? When they were still in your blood, it looked like liquid. But when you clump them all together, now all of a sudden it's a solid clump of these bad guys. And, of course, antibodies. Well, now a macrophage can see it, walk, and eat it. Then
What glues it together?
Huh?
What glues it together?
The antibodies.
Oh, the antibodies.
Yeah, see, this Y shape here glues this one to this one, and this Y shape here glues that one to that one. Got it? It is a big network of gluing it. All right? So that is the P of plan. L is for lysis. Now remember, lysis means to break open a bad guy. Do antibodies break open anything? No. However, antibodies will make complement protein get released. Got it? By the nearby cells. And those nearby cells, their complement does 3 things. It will MAC attack, lyse a bad guy, it will increase inflammation, the cascade effect, or it will make it tasty for a phagocyte, opsonization. So that's why they said, let's just use the L of lysis in this word plan, because there is no word you're going to think of that's P-C-A-N. Got it? Pecan, I guess. So they call it plan. 10-4? All right, what's A? Agglutination. Like precipitation, I'm gluing bad guys together. But this time, I'm gluing together big things called red blood cells. Got it? But I'm still gluing it together so the macrophage knows who to eat. Okay? And last but not least is the N, and that's neutralization. What does it mean in military terms when you neutralize the threat?
Stop them.
Yeah, but have you killed them? Not necessarily, but you've made sure that they can't be a threat anymore. What if you took away their weapons? They wouldn't be a threat. 10-4? Got it? What if you blinded their radar system so they didn't know where to shoot their rocket to? You've eliminated the threat. You've neutralized the threat. Got it? So, what is this? Is a virus with little spike proteins. what if we covered the entire virus with antibodies? Could any of those spikes land on one of your cells and infect your cells? No. So I haven't gotten rid of the virus, but I've made its impact neutral. Got it? It cannot make you sick because it cannot enter your cell. It's been coded. And of course, when it's coded, it's also going to get eaten. But that's neutralization. Because we don't kill anything with an antibody. Okay? That's important. Does that make sense? There's your PLAN. There's your plan of attack. Now the next question says, complement and agglutination help you to eat the bad guys, but in different ways. Well, what does complement do? This is complement to help you eat a bad guy. Opsonization. Complement will coat a bad guy and make it what? Tasty. And your macrophage will eat it. Got it? It's like a plain donut versus a glazed donut. You put the glaze on it, ooh, I'll eat that. 10-4, that's the antibodies. You might say, wait a minute, aren't you eating the antibodies while you're eating the bad guy? Yeah, but that's okay, it's just protein. We'll make more and they can use it. Got it? Okay. What is the other one? Besides complement? Agglutination. Well, what am I doing when I'm agglutinating or precipitating? Putting bad guys together so they're easier for the phagocyte to see and eat. Got it? So either we make it tasty, opsonization, or we glue it together to make it easier to see. Does that make sense? They both aid in phagocytosis. They both make the phagocytes eat the bad guys. Okay? All right.
I do have one quick question. Yeah. With, let's say, an antigen is getting covered in the antibodies.
Right.
There's always going to be a complement protein to make it more tasty to the phagocytes, or like,
I think we have so many things that we can use that maybe if the complement got there first, it's going to make it tasty. If the antibodies get there first, it's going to make it tasty. Got it?
Yeah.
So
essentially, they do the same thing.
It's right. Just exactly the same thing. They're different. Yeah. It's just an antibody is a Y-shaped protein. Complement is just a little blob. You know. So, and it's made by a different kind of cell.
And the complement protein won't stick anything together. It's just as
right. Complement won't stick anything together.
Yeah, it's just the flavor.
Okay. Yeah. Good question. But far deeper than we need to get. Okay. All right, we got that. Now, natural and passive. I like this. Natural, active, and passive. All right. Here we go. Let's keep it simple. All right? If it's natural, it happens in nature. If it's artificial, there is an injection involved. Got it? A syringe with a needle on it. That's not natural. Okay? Unless you count the big mosquitoes that are running around here. Cool beans? Okay. Passive. Somebody else made the antibodies for you. Active, you have to make the antibodies. Okay? All right. Now we're going to use those 4 words to make 4 different kinds of immune situations. All right. If it is active, natural, you got sick. I know you want to look at this one, look at that one. If it's natural and active, you got sick, you got better because you made the antibodies. Isn't getting sick natural? And it's active because you made the antibodies. If it's artificial and active, it's artificial. You were given a vaccine. Didn't you have to make the antibodies against it? Yeah, but it was a shot, not natural. Okay? Natural and passive. Mom sends her good antibodies to the baby to help the baby fight off bad guys. Mom can do it through her placenta. Mom can give antibodies through her milk. But mom's making the antibodies. Why? Because the baby's body is not ready to make a lot of antibodies yet. Got it? Okay.
Is that the only natural passive? Is from mom to child?
What are you thinking of?
Like maybe let's say that one case where you took somebody else's blood
Mhm.
to get the antibodies
From their blood,
from their blood, that would be
that's passive.
passive.
Because they made the antibodies.
Yeah.
Got it?
Well,
If
But
you
it's
take somebody
artificial
else's
because you're
blood
putting it in.
with antibodies in it, they made it, you didn't, it's passive. But it's artificial because you have to be injected with it.
what if
And this is like a Rogam shot.
what if someone like you were next to someone who had a cold and then you caught the cold?
Okay.
Would that be natural passive?
Yeah, no, it's not passive. Because passive is not the cold. Passive is how do you fight the cold. You're making antibodies, so it's active. If you have to make antibodies against the cold you just caught, it's active. You're making the antibodies. When somebody coughs on you, they're not giving you antibodies, they're just giving you the bad guy. Does that make sense? They're not giving you antibodies. But there was a case where a doctor had just survived Ebola, and the nurse came down with Ebola, and so they gave her his blood. Why? Because his blood, since he survived, was full of antibodies against Ebola. And that way, it would fight the Ebola for the nurse without the nurse's body having to create antibodies. Got it?
They would just keep giving her the blood until
Well,
she's better
I don't think it was every time, but I mean, they just gave her the blood and there was enough antibodies
to fight.
to go after the bad guys, yeah. Okay? And maybe by that time, her own body could make antibodies. But we want to nip it in the bud before it takes over. That's why the doctor almost died, because his body couldn't keep up making antibodies against the Ebola. There's so much of it. Does that make sense? Remember, you got that 5-day delay before you get, and you make it smaller. Well, in those 5 days, the Ebola might have tripled in number, quadrupled in number. Cool beans? So that's how we tell those 4 apart. What's the next thing? Oh, type 1, type 2?
Type 2.
Yeah, okay, that's easy. Let's go. Type 1. Well, there's 2 kinds of type 1. It's basically hypersensitivity. Immediate hypersensitivity and a release of histamines. Got it? So, because it's the release of histamines, who's involved? Because IgA tells your mast cells in your skin to release that, or it tells your basophils in your blood to release that. Okay? All right. So, what is this? Hay fever, asthma, eczema, upset stomach because you just ate some spoiled food or something. Got it? That's what that is. You immediately release histamines to try to take care of business. So you're going to end up with some kind of inflammation.
And IgE is the one that you ingest, right?
IgA.
Oh, that's
Okay. Now, what's anaphylactic shock? This is where the bad guy, the antigen that you don't like, got into your blood. It's not just in your nose. It's not just in your skin. It's not just in your stomach. It's now circulating in your blood. Well, what's in your blood? All of your basophils. And when IgA is released, every basophil gives histamine. And every blood vessel goes boom like this. Got it? So where's your blood pressure? Straight down to 0. Got it? And it's also going to constrict your bronchioles so you can't breathe. Because again, do your lungs know who the bad guy is? No, I'm being attacked, so let's cut off his oxygen supply. Got it? And so, what do I need? An EpiPen to constrict my blood vessels and jumpstart my heart in case it stopped. Make sense? All right. So, anaphylactic shock actually comes in 2 varieties. Anaphylaxis, which is something you've eaten, and septic shock, which means a bacteria has gotten into your blood and is releasing a toxin that also causes IgEs to tell the basophils to release histamines. The result's the same. Blood vessels dilate, blood pressure down to 0, heart stops. Okay? All right, type 2. Type 2 doesn't have anything to do with histamines. It's all about making antibodies against the bad guy. Okay? Making antibodies. And of course, some of the worst ones, is a blood transfusion mismatch. your IgMs are going to glue up a whole bunch of red blood cells, and that's going to be a lot of clotting. Okay? All right. Type 3. This is an immune complex reaction. You're making antibodies, but that is going to now complex into more and more glued up situations. Okay? It's going to form complexes that deposit in certain tissues. Got it? And is very, difficult to get rid of. Like if it's in your joints or if it's in your kidneys. Okay? Lupus is an example of some really, that's number 4, but lupus is a really bad example because it can attack your brain and it can attack your lungs, it can attack your skin, it can attack your joints, different parts, okay? But it's characterized by creating antibodies that are anti-DNA antibodies. Well, gee whiz, every cell in your body has DNA in it, so it's going to tell your T cytotoxic cells to kill anything with DNA inside it. That's pretty bad, okay? And number 4 is hypersensitivity from things like poison ivy. Now, how is this different? It has nothing to do with histamines, nothing to do with antibodies, but 100% it turns your T cytotoxic cells on. And when they attack your skin, that's the blistering. Got it? I've got poison ivy on my skin, and my T cytotoxic cells say, well, let's kill your skin. And that's the damage. Got it? And I know this because when I first touched it 20 years ago when we first moved here, I had rash, and I'm going, uh-oh, I better take some Benadryl. It didn't work. Next day I took more Benadryl. It didn't work. After 3 days of taking Benadryl, I said, I got to go to the doctor because it was like here and here. You can't help it go like this and, like that, and all of a sudden, wherever your fingernails have been, all of a sudden, like, I didn't do this, that would have been, woo, you wouldn't see me anymore. So the doctor said, you've been to poison ivy, haven't you? I said, yeah, I don't know where it is. See, that's the problem. You touch it on Saturday, you don't see the rash till Monday. So I've already forgotten where it is. I picked it up. Therefore. And he said, yeah, I bet you tried Benadryl too, didn't you? I said, yeah. He goes, that's not going to work because histamines aren't involved. It's your T cytotoxic cells. So what does he give me? Cortisone. Cortisone. Big cortisone shot, to nip it in the bud, and cortisone cream to bring it down. So you can suppress the white blood cells. That's what cortisol does. It's an immunosuppressant. So it's going to stop the cytotoxic cells from attacking your skin. But that's why Benadryl, an antihistamine, won't work. Does that make sense? And that's basically all we need to know about these hypersensitivities. Okay? So, histamines, antibodies, antibody complexes, and T cytotoxic cells. See how that works? Okay. Alrighty. Transplants and autoimmune diseases. All right, are the transplants in here? Yeah, here they are. Here's the transplants. Okay. When we say transplant, that means you give me an organ. Got it? But can I give myself something? Yeah, a skin graft. Got it? If I burned this, they'll take thigh skin and put it here. Got it? Okay. So that's why we call it graft. Autograft means from yourself. That's from this part of my body to this part of my body. Any rejection? No. What's rejection, by the way? Your T cytotoxic cells attacking the new tissue because you don't belong here. Well, it's still you, so they leave you alone. Alrighty? Allograft. The word allo means from who?
Alien.
Okay,
Right.
not an alien. Another one like you. Well, who's exactly like you? An identical twin. Why? Because an identical twin was one baby that split into two babies and both grew up. You have the same genetics. Got it? That's why you're both going to be 6 feet tall, you're both going to be male, you're both going to have the same color eyes. You know what I'm saying? Like the Property Brothers. Got it? Okay. Now, I'm sorry. ISO, what are you pointing at? ISO means identical twin. I was pointing at the wrong identical twin. Allo is any other person besides your identical, because allo means the other. ISO means the same. I apologize. I had to get my wife to the airport real early this morning for the flight, and I've been up since 3 o'clock, so I am tired. All right, ISO means the same. That's identical, same people. Allo means the other person. That could be your brother, could be a cousin, could be the guy down the road. And isn't that what happens when you need a kidney? It's not going to be from your identical twin all the time, right? Could be somebody else in the family, somebody else down the street. 10-4, that's an allo. Now, the xeno, that's an animal. Because xeno means total stranger. And not stranger as in person, but total stranger as in species. So that would be like getting pig skin or pig valve. Does that make sense? Okay. And which one is going to have more rejection? This. Got it? Well, what do I give you? Immunorejection medicine, kind of like a different kind of cortisol that basically tells your white blood cells, especially T cytotoxics, down, boy, down. We don't want any more. Got it? But what's the side effect of not having T cells and B cells to fight for you?
Can't fight the bad guys.
You will catch just about anything else. But it beats the alternative being dead from kidney failure. 10-4, you just got to be extremely careful. And so, who were the most susceptible people when COVID hit? Those immunocompromised people. People who were on cortisol, people who had just gotten transplants, because they've already had their white blood cell suppressed. So there was nothing around to help you fight off COVID. Does that make sense? And that's what happened to a lot of people.
I was just gonna throw in there too. My wife, when they were teaching her in nursing school, after transplant, they put you in like a special room.
Yeah.
That's basically sealed off to
Yeah.
make sure you don't have any.
Nothing else can get in there to make you sick. Yes, which makes perfect sense, because that's what you're doing when you get a transplant. You've got to knock out the person's white blood cells, because they will immediately start attacking the new kidney. Well, gee whiz, you were probably on the kidney waiting list, for 10 years, and you want that kidney to be destroyed in 3 weeks while it's inside you and start all over again? No. Got it? Now, that's why, I should say, that whenever you need a transplant, the first people they look to is family members, so you can be as close as possible in match. Got it? Then they look at other people with at least the same blood type. Got it? But yeah, that's as close as you can get. You're always going to have some rejection, all right? Because it's not your identical twin. All righty, did that help? Okay. And let's see, autoimmune diseases. Okay. What's an autoimmune disease? Where your immune system, your B and C, cannot tell self from non-self. They think you are a bad guy as much as a bad guy is a bad guy. Got it? Every part of you is an antigen that needs to be attacked. Alrighty? And so we create antibodies that are auto-antibodies. They're against you, antibodies that don't like you. They don't like self. Alrighty? And of course, your cytotoxic cells will attack those tissues and organs and destroy them. Is that a good thing? No. All right, we got the worst kind, which is SCID. No B and T cells. Got it? But you got none of this. What are you going to be attacked by? Everything. Okay? And that's kind of what this kid had. That's the boy in the bubble, the famous boy in the bubble. All righty? Can you imagine growing up inside this, never having touched your parents? They want to hug you. They got to put their hands through these things with gloves on the inside. And if you want to get food, they have to put it through a lock, an airlock, to get to it. All right? And then, of course, you got AIDS, where you've acquired immune deficiency because the HIV virus kills who? All the helper cells. Got it? The HIV invades the helper cells and other things like macrophages and dendritic cells. So when you start destroying the guys whose job is to help protect you against bad guys, guess what? Any bad guy that comes along is going to kill you. Alrighty? Now, it's a retrovirus. What does that mean? Instead of DNA inside its capsule, there's RNA. So it shoots its RNA into your cell, which then has to be reversed back into DNA. Then that DNA can hijack your DNA. Got it? The viruses that we talked about earlier, its DNA hijacks your DNA, but this has to be switched from RNA back to DNA in a reverse transcription. Got it? So because of that, now that we know that we can, I guess I don't have that in here. Because we know that, what can we give an HIV patient? Reverse transcriptase inhibitor. So if we can inhibit the RNA from being turned into DNA, he can't hijack you. Do you still have the virus in you? Yes. Is the virus still making you contagious? Yes. You can't have unprotected sex, you can't donate your blood to the blood bank and stuff. Got it? Just to be safe. Does that make sense? Okay. See, that's Kaposi sarcoma. That's another very rare cancer that HIV patients get. Hey, when you destroy all the T cells, T helper cells and whatnot, guess what? Your regular immune system cannot fight cancer. You see, this is a very rare cancer because all of us with healthy B and T cells kill this as soon as it grows. That's why we don't have that. But you get rid of the helper cells, all of a sudden, boom, that shows up. But that's why it's rare for us, because we kill cancer cells on purpose. Got it? But not if we're immune compromised. Okay, and then as you get older, you fall apart. That's me. Okay. Hey, how are we doing? Any last minute questions from the peanut gallery? No? Okay. Well, that's it then. Thank you.